Hey folks, today's topic is evaluating limits using tables. So if you remember last time, we looked at evaluating limits graphically. So we looked at where did the graph intend to go, even if sometimes it got there and sometimes it didn't get to where it intended to go, but that was our goal. So that's the same thing that we're doing here. At the end of this, we should be able to look at a function, complete the table, and then evaluate where that function, where that limit is headed by the table. And eventually I'm going to get to the spot where I'm just going to give you the table because, I mean, I want you to practice how to do it on the homework, but on the test, I know I'm going to just give you the table filled in just because it takes a while to fill it in, but I think it's important to know where that table feature is in your calculator. So, all right, so we're asking here, remember what this notation means. This is saying what is happening to my function as x approaches 2. So my x values should be approaching 2, and then I'm going to look at what my function values are doing. So I'm going to use a table to complete this. So I want to first I have to tell my calculator what my function is. So grab my calc. Go to y equals, I'm going to input the equation, 5x minus 2. Now, if you want to graph, feel free. There's no real need to graph because it's not helping us figuring out, can you tell what's happening? I mean, you could probably kind of predict where that's going above 2. But we're going to use this. You're going to use our table to set this up. So there's two things that we're going to worry about here. We're going to worry about table setup, and we're going to worry about table. Notice they're both in the blue, so I'm going to hit the blue button first. So there's my table. Now right now, so I want to center, what are we approaching? We're approaching x approaches 2. So I want 2 to be in the middle of my table. So I kind of have 2 in the center. The problem is it's kind of tough to predict what's happening from either side. So what we're going to do, if you remember we did this with graphs, we don't look at the whole graph. We just kind of look near the x value that we want to evaluate. So, or the limit that we're trying to approach. So I'm going to try to get this table to look at what's happening really, really close to 2. Now, I know 1 is fairly close to 2, but in terms of all the numbers between 1 and 2, it's not actually that close. So we're going to change the scale that our table is going to count by. So that's underneath table setup. So I hit second, table setup. Now, table start is where you want to approach. So that's the limit that you're approaching. So x approaches 2. And then delta table should be something fairly small. I usually pick something like 0.01. You can pick whatever you want. The smaller that value, the more accurate your prediction will be. But usually 0.01 is good enough. So now I've set these two things up. You don't have to worry about those. Now I go back to my table, and I now have the 2 is where it starts. I want to center that. So I'm going to move up a little bit and then back down so that my highlighter is on the 2. That's the place that I'm approaching. So these are my x values. I'm approaching from either side. And then these are my y values. We're approaching from either side. This one's pretty straightforward, but I always pick an easy one to start us off. So now I'm going to take these values and I'm going to transpose them. I don't know what that right word is, but I'm going to put them in the table. So here we go. I'm going to slide this off a little bit so I have room to write. I'm going to start on the low end of my chart, which is 1.97. And go to the high end, which is 2.03. And I'm going to do the same thing for my y values. Now I got to put the y values in there. 7.85, 7.9, 7.95, 8, 8.05, 8.1, 8.15. So the limit is where the function is intending to go, not where it really went. Now, sometimes those are the same answer, but that's not what we're looking for with the limit. We're looking at where did the graph intend to go. So I'm going to track in. This is the limit from the left. 7.85, 7.9, 7.95. Where were these things headed? These were headed to 8. If I were to make a prediction, in other words, if I covered this up, let me grab something that I can use to cover up. If I covered up this half of the table and I said, you have to make a prediction on what number you think is going to come after these three numbers, 785, 79, 795, I would predict that 8 would come next. Notice I covered up what's happening at 2 because a limit is not what's actually happening, it's where it's approaching. So now I'm going to cover up the other side, and I'm looking at these three values, 8.15, 8.1, 8.05. And I'm going to track in, and I'm going to make a prediction. 8.15, 8. I think this is also going to head towards 8. So what did we learn about limits? When one side of the limit is headed towards the same place as the other side of the limit, that's the same as the overall limit. So my limit here is 8. Now the function value is a different question. This is what the graph intends to do. This is asking you, what did the graph actually do at x equals 2? So I like to circle that here. What's actually happening when x equals 2? It reaches a height of 8. So graphically, what does that look like? When you have the graph approaches 8 and the actual point is at 8, that's something we talked about last time. That should be a continuous. The function is continuous at x equals 2 because the limit and the function value are the same thing. All right, let's try another one. Now this one, obviously, like I said, I picked one that was really easy to start off with, pretty straightforward. So going to the next one, we want to look at some tricky scenarios. All right, so we're going to start off. All right, so there's two types of calculator people. You either have the fancy operating system or the old school operating system. If you're old school, make sure that you use lots of parentheses. Parentheses around the top, divided by blah, 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 parentheses around the bottom, around the root. I have the new fancy operating system, so I'm going to put my calculator in its fraction mode. Square root of x plus 1, then push out of there and put your minus 1 in there because the minus 1 isn't underneath the root. Okay, now if you want to go to the graph, you can. If you want to go to the table right now, you can. But I would recommend setting up your table in a way that makes sense. If I go to my table now, this isn't any help because where am I approaching? 2. And we're supposed to be approaching x approaches 0. So go to your table setup first. Your table start should be whatever your limit is, and then I leave delta table to be 0.01. Once in a while you'll have to mess with that, but most of the time you won't. Once you have your table set up, then you can go into your table. Move your cursor so that 0 is in the middle. So that's where we're trying to approach. So I'm going to now put the data from the table into from the calculator onto my paper. So negative 0.3, negative 0.2, negative 0.01, then 0, 0.01, 0.02, 0.03. I think I said that wrong at the beginning. Sorry if that messed you up. Now I'm going to put in my y values. I'm not going to I don't want to write out all those decimals. I guess I can fit them. 3.9698. 3.9799, 3.99, error, 4.01, 4.0199, 4.0298. Okay, now that we have this data in the table, we can start to figure out what the limit is. So I'm going to approach, cover up one side, coming from the left. What number would you predict would come next? 3.96, 3.97, 3.99. I would clearly predict 4. Then I cover up the other side, cover up the limit that we're going to. We're approaching that place. So as I approach this side of the table, we're approaching the value of 4. Then you can step back, and now you can talk about the overall limit. The limit is what the function approaches from both sides. So this side from the left approached 4, from the right approached 4. That means that my overall limit is going to be 4. This is asking you what's the actual function value. So I'm going to now box in what's actually happening at 0. There's no value there. There's no point. When I plugged in 0 into the table, I got an answer of error. So that means that there is no function value there. You could write undefined. I'm going to write DNE. Okay, so what does that look like when a graph comes together, when a graph meets, but there's nothing where it meets? See if you can remember from yesterday. Pause it if you can't. See if you can remember the graph met, but there's nothing there where it met. This is a hole. This is what a hole looks like graphically. All right, here we go again. I've got my function. Now this time my function is a piecewise function. So the tough part here is to show you how to input this into your calculator. I hope you could sketch that, but if you can't, let me show you how to put this in your calc. So you're going to put parentheses. Actually, I'll highlight it on the paper first. So you put parentheses here, and then you put a divide by in the middle. So I would put parentheses around this when I type it in, divided by parentheses around the second piece. So my first equation would be the top part. This would be my second equation. So the quantity of negative 5x plus 6, close it, divided by the parentheses, x, okay, not equal to. Everything with your less than, greater than, equal to's, not equal to's is underneath this option here called test. Test is in blue, so I'm going to select the blue button first, and then you'll see that there's a not equal to option. Close your parenthesis. Go down to my second function, x plus 4, divided by the quantity x. Now I go into test again, equals 2. And this time I'm going to cut to the chase. I'm going to save myself some time. I'm going to go right to table set to begin. So where should we be approaching? My table start should be 2. My delta table should be still something very small. Now I can go to my table. I always want to set it up so that 2 is in the middle. Okay, so your chart now, you have 3 different columns. Normally we only have 2. This is my x's. These are my x's. These are my y1s, and these are my y2s. So what you have to do here is you have to follow along, and then you jump to there, and then jump to here. Okay, so all the errors are the parts that don't count. So really, if you could, you should squeeze this table into these 2 columns, you should squeeze them into 1 column. So basically that 6 should slide there. Now your calculator can't do that, so we have to be able to interpret it on our own. So I'm going to move this to the side, fill in my table. I mean, I could have filled in the table pretty well right off the bat, considering we know that 2 is going to be the value we're approaching, and I'm always counting by 0.01s. So this would be 2.01, 2.02, 2.03. And then going the other way would be 1.99, 1.98, 1.97. Okay, so now, like I said, from your chart here, you want to use the coordinate that is actually there. Now, if they both say error, you would write DNE for both for that value. But we have points here that then jumps to this column and then goes down here. So I would have what? Negative 3.85, negative 3.9, negative 3.95. Then I jump to the other column, 6. Then I jump back, negative 4.05, negative 4.1, negative 4.15. So I want to now cover up half of the story and make a prediction on what I think would come next if I came from this side. Negative 3.8, negative 3.9, negative 3.95. I think this is headed to negative 4. Then I would cover up this side. Now, you don't have to actually get a piece of paper to do that, but in your head, you want to look at what's happening as you approach. Now, if you have a longer table, that's fine, but you don't need to go all the way down. You just need to go near the place that you're trying to approach. So this is also headed to -4. Since these are both headed to -4, I have an overall limit of -4. Remember, the limit isn't where it goes. The limit is where it intended to go. And so this side of the table and clearly meant to go to -4. This side meant to go to -4. So the function meant to go to -4. Now, what really happened? That's where I circle this. This is what's actually happening. And so my function value is actually at 6. All right, so pause if you have to. Let me finish my little hint here. But try to think, what does this graph look like? What would this look like if you had this on a coordinate plane? So both sides of the branches are meeting, and then there's another point somewhere else. All right, let's see how you did. So if my graph meets, but there's nothing there, that's a hole, but then there's a point somewhere else, that's a holy jump. And if you're having a hard time picturing these, grab your notes from last time and look back at the graphical version of each one of these situations. Okay, I'm going to encourage you to pause here and try to do this one on your own, and then we'll check it out together. All right, let's see how you did. So I would start off with my function, clear out this old stuff. This is not a piecewise, so I don't have to do anything fancy. I'm going to type this one in old school just so we can practice for those who don't have the fancy calc. X to the third minus x squared plus x minus 1. Close it, divide by another parenthesis, x minus 1. Where are we approaching? We're approaching 1, so I'm going to go to my table, setup. I'm going to approach, my start is going to be 1, and then I can look at my table. Now don't forget, it always skews it so that 1 is the first thing you see. You want to push that up and then come back down so that's in the middle. Now I'm going to put all this data into my actual chart. 0.97, 0.98, 0.99, 1, 1.01, 1.02, 1.03, 1.9409, 1.9496, 1.9604, 1.9801, error, 2.0201, 2.0404, 2.0609. So if you've done this once at least, now from here on out, I can tell you, you don't have to even do the table anymore. If you can figure out, now I would still recommend maybe drawing the little arrows and stuff like that, but if you can figure this all out just using your calc, I am definitely okay with that. Like I said on the test or PQs, I'm going to give you a filled in table. You'll see that on the back of the homework. But I want you to at least practice how to type this into your calc and then use your table. You don't have to actually transcribe it onto your notes. Okay, what would be a good color here? How's about, I have like a nice, just did pink, so I can't do pink again. How about a nice orange? How about an ugly brown? How about that? Okay, where is this going? I'm looking at these three. 1.94, 1.96, 1.98. That clearly wants to head to 2. 2.06, 2.04, 2.02. That also wants to go to 2. So they're both approaching 2, so my overall limit would be 2. My actual function value at 1 does not exist. So my graph meets, my graph heads to the same place, but when it gets there, there's nothing there. So what's that called again? That's a hole. I'm going to encourage you to try to do the next one on your own, at least. Yeah, try to do the whole thing. See if you can do the whole thing on your own. So pause it. I'm going to start up in a second here or two. Okay, let's see how you did. clear it out. Remember how this works? It's parentheses divide by parentheses. So parentheses 6 plus x squared, close it, divide by the quantity x. Now I need a greater than or equal to underneath test. Greater than or equal to -3. Then 2x minus 3 again, divided by, this time we're going less than -3. Table setup should be at -3. Oops. Center it, so -3 is in the middle. Yeah, ooh, this one's going to be an interesting one. So let's see. Remember how this works. You really want to take these two columns and merge them into one, where the number will always replace the error. If both columns have an error for a specific x value, then it will always be error. So now, fill in my little table. -3.03, -3.02, -3.01, -3, -2.99, -2.98, -2.97, -9.06, -9.04, -9.02, 15, because I'm jumping to the other table, 14.94, 14.88, 14.821. All right, let's approach it. Let's see where you're headed. So coming from the left, just looking at these three boxes, I would predict that we're headed to -9 for sure. These three boxes, I would predict that we're headed to 15. Uh-oh. So let's go back to what we did last time. Your one-sided limits are not equal. As I come in from the left, I'm going to -9. My graph's going down here to -9. As I come in from the right, my graph's going up here to 15. What kind of limit is that? It doesn't exist, right? For us to have the same limit, both of us have to head to the same place. So you have to go to the McDonald's in Fruitport, and I have to go to the one in Fruitport. If you go to Spring Lake and I go to Fruitport, we're not at the same place. So this time my limit does not exist. Now the actual function value doesn't care about whether the limit exists or not. It's saying what's actually happening at -3, and what's specifically happening there is a y value of 15. All right, so what does that look like? What does that look like when my graph doesn't meet? They both head to different spots. We call that a jump. I'm going to have you try, let's do the next one together. Not that you couldn't type it in. You can do all that part on your own if you want to pause and do that and fill in your table. But I think evaluating it is kind of sneaky. This time I'm going to do it with Fancy Calc. I'm heading to 3, not -3. Okay, so (2.97), 2.98, 2.99, 3, 3.01, 3.02, 3.03, 5,555.6, 12,550, or sorry, just 500, 50,000, error, 50,000, 12,500, 5,555.6. So let's approach from the left first. Now remember, you have to make a prediction here. So you have to guarantee with pretty much certainty exactly what that number is. Like up here, it was pretty obvious that this is headed to -9. I think all of these we've been able to look at and find a prediction that's pretty darn accurate. Now, I know this number is going to be bigger than 50,000, but I don't know where it's going to hit. I can make a decent estimate that it's going to hit maybe around, I don't know, 75,000, maybe somewhere in that range, but I can't say with certainty that it'll be exactly 75,000. Maybe it'll be 80,000. Maybe it'll be 70,000. But what do we know? So we can't say exactly where it's going, but where did we say it's definitely getting bigger. This side is definitely getting larger and larger and larger over time. If you want to, I can show you on your calculator what I was talking about earlier about changing your table setup. Watch what happens when I change my table setup. I'm going to make it 0.01 this time. Oops. 0.001, I mean. You don't have to do this, you can just watch. But watch what happens to my values. Now, remember, this is your scientific notation. That's 5 with 6 zeros. That's 5 million. So now we're headed to 5 million. That's because I'm getting more and more accurate, more and more close to 3. And if I even get closer, see how nasty this gets. 0.0001. Oh, I got to go back up here to change that to a 3. Now we're headed to 50 million. Okay, so as I get more and more accurate, what happens to the values that I'm approaching? They get larger and larger and larger and larger. So it does make sense that we would indicate that this is just, I don't know where it's going. I just know it's getting bigger and bigger and bigger. And we could make the same argument from the other side. Now, sometimes these have a negative in front of them, so you would be approaching negative infinity, not positive infinity. But no big deal there. We know that there's the same. I mean, it just doesn't matter which way we're going. So, if you're approaching the infinities, do you have an overall limit? You do not. You do not. Even though they're both headed to the same infinity, we would still say the limit does not exist because you can never actually get to infinity. Okay, you can intend to go to infinity, but it's not an actual location. It's not a point. Okay, so let's evaluate the function at 3. That also does not exist. So let's think yesterday, or last time I should say, what happened. What kind of graphical situation was it when the limits kept getting bigger and bigger and bigger, and then there was still no function value there? If you don't remember, grab your notes from last time, look at some of the pictures that we drew, and take a guess. What'd you come up with? Hopefully you said this is an asymptote. This is an asymptote. So when the limit does not exist, remember we talked about this before. When you're continuous, when you have a hole, when you have a holy jump, your limit will always exist. Those are the 3 scenarios for which a limit could exist. The 2 scenarios for which a limit does not exist are a jump or an asymptote. So I'm going to actually put that on the side here. These 3 scenarios, the limit exists. Continuous, or a hole, or a holy jump. Your limit is going to exist. Now I'm going to highlight for all 3 of these. I'm just going to do these. Limit does not exist. The next one, the limit's not going to exist as well, but it's just kind of a weird one I like to show. It's not one that I'm going to hold you to on any sort of assessment. Maybe a PQ, because you can use your notes to look back, or you can ask me for help. So let's look at this last scenario. So this is sine of, I'm going to do old school so I don't have to type as much. Make sure your mode is in what mode? Whenever we graph, our mode must be in radians. So now I'm going to go to my table setup. I'm approaching 0. I'm going to go back to 0.01. Go look at my table. So we would have something like negative 0.3, 0.02, negative 0.01, 0, 0.01, 0.02, 0.03. And then we get negative 0.9405, 0.2624, I ran out of room, 0.5064, error, negative 0.5064, negative 0.2624, negative 0.9405. Okay, so I can see that there's some sort of a symmetry going on here, but if I asked you to cover up half of this and make a prediction on what you think would come next. So we went from a negative to a positive to a bigger one. So kind of you could make an assumption that it's going to be something bigger, right? I mean, at least it's going from a small number and it's growing a little bit there, but could you tell me what that next number is going to be? With pretty confident, could you tell me what that? No, you couldn't. And watch what happens. I'm going to adjust my table setup again. I'm going to go to 0.001. And look, it went back to being a negative. So this time it went negative 0.3, which doesn't fit with our data. Then it went up to a positive. Then it went back to a negative. This is what we call an oscillation. So as this approaches, I don't know what's coming next. As we approach from this side, I also don't know what's coming next. So I definitely couldn't predict where the graph intends to go. So I would say that's a DNE. There is no way the limit approaches. The error also means that there is no actual function value. But this isn't an asymptote, because an asymptote, you can see that there's a pattern that's somewhat predictable. I know these numbers are continually getting bigger. And you remember I adjusted my delta table to see even closer and closer and closer. When I adjusted my delta table here, it got less predictable. And this is called an oscillation. I just think it's a cool function. Let me show you graphically what it looks like. So I'm going to set my window. You can just watch, or you can mess with yours if you want to. I think it goes from -1 to 1. Let's go from, we're doing radians, so let's go from -2 pi to 2 pi. Counting by pi over 4s. Check this guy out. I'm going to adjust it again. I'll go from -2, let's say. Check this out. Here comes my graph. And then it goes infinitely crazy in that mess in between. So your graph can't possibly draw it, because you should, let me adjust my window again, make it even smaller. This graph goes up and down infinitely many times. This should really be like a solid black mass of points. Like this thing just comes in like this, and then it just goes crazy in there, and it's just, everything is solid. There's infinitely many points, infinitely unpredictable points, and then it just comes out nice and smooth the other side. But everything in there just goes absolutely nuts. So it's kind of a cool function. There are a number of functions that do that, different oscillations. Let me see what that looks like on Desmos. I've never played around with Desmos with this function, so I'm gonna check out a quick Desmos here. So y equals sine of 1 over x. What would be a good window? What did we say, from like -1 to 1, right? -1 to 1, and my y value, -1 to 1. I'm going to square it. I hate it when it does that. What do I want to adjust here? I can just, you get the idea. So look at this thing. So look, these points are just like these random points that are just all over the, look, it has 2 y-intercepts. So this graph goes in crazy. But it's crazy how beautiful it is outside of that, like how smooth it is and predictable. And then once you get in within that boundary, I should probably try to figure out where that boundary is at some point. and then it just goes nuts. It's just solid mass of unpredictable points all over the place. So, okay, folks, at this spot, I'll stop you and encourage you to take a look at the homework, and then let me know what questions you have. We can work on it together.